Hello.
Hello.
Should I start or?
Madam, please begin. We are live.
Okay, sir. Sir, I'll start. Good morning, everyone. Myself, Dr. Bhumi Bhatt, Assistant Professor in Electronics and Communication Engineering Department of Parul Institute of Engineering and Technology, Parul University. I take this opportunity to welcome Dr. Balwant J. Makwana, sir. He is Assistant Professor in Electronics and Communication Engineering Department from Government Engineering College, Rajkot. We will be presenting the webinar on the topic Fundamentals to Research Advances in Antenna Design. Dr. Balwant sir has more than 12 years of teaching experience in different government colleges. He has achieved his doctorate degree from Gujarat Technological University and is expert in the field of antenna designing. He has completed his master's in communication systems from LD College of Engineering, Ahmedabad. He has completed his bachelor's in electronics and communication engineering from VVP College of Engineering. He has filed 2 Indian patents in the field of antenna designing. He has published and presented more than 18 research papers in various international and national journals and conferences. He has achieved Best Paper Award in IEEE Indian Antenna Week. He has taken various trainings from IITs and NITs for getting expertise in this related domain. Now I request Dr. Balwant sir to please share your expertise in antenna designing with us. Thank you, sir.
Thank you,
Balwant, sir.
ma'am.
Yes, sir.
Okay. Thank you, ma'am. So, thank you for your kind words. I'm starting my seminar, right? So, my screen is visible, I hope. Is it visible?
Sir, you are not visible.
My screen is visible.
Your screen is visible, sir. You are not visible.
Uh, I don't know how. So, let it be, whatever.
Okay, sir.
So, I will start my presentation, right? So, my today's topic is fundamental. Okay, Madam has introduced me. I am Professor Dr. Balwant J. Makwana. I am from Government Engineering College, Rajkot. And today's my topic is fundamental to recent advances in antenna design. So we are going to learn the fundamental as well as what are the recent advances in antenna design. So this is the outline of my presentation. First of all, I will do some introduction, then we are having some application. So we are moving first to application so that you know that which kind of antenna or what are the things which are used in antenna field. Then we'll see some fundamentals of antenna. Then we'll see some antennas which are, or you can say, the conventional antennas and its design. Then if time permits, we'll see the measurement and we'll conclude our session. So let us start with the so these are the antennas for various applications. You know the radio station like AM and FM station. So AM station is there. It requires the frequency of operation is 530 to 1620 hertz. So this kind of radio station is using the lambda by 4 monopole antennas. So simply it is using lambda by 4 monopole antenna for this frequency, that is AM modulation and FM. For FM modulation, we know that we are having 88 to 108 megahertz, that also using the monopole antenna. Then the cell phone antennas. So cell phone technologies are having a different frequency range like GSM 900, GSM 1800, CDMA, 3G, 4G. So we are most of the time we are using monopole antenna or normal mode helical antenna, microstrip antenna, then various other kinds of antenna for cell phone technology. Then in a cell phone it means we are using mobile. That cell phone will have a different technology. In cell tower, we are using the array of monopole antenna, array of dipole antenna, microstrip antenna, and so on. In satellite and defense communication, we are using almost all kind of antenna. We use microstrip antenna, we use horn antenna, spiral antenna, helical antenna, and reflector antenna, which will provide most of the gain. Yagi-Uda antenna, low periodic antenna, etc. So we'll see some of the example. Like this is one of the missile, and it will have different kinds of antenna. So you can see that it will have a radar altimeter antenna. So what exactly is altimeter? Altimeter will find the uh, altitude of uh, any, like if it is deployed on the missile, it will find the altitude of the missile, or if it is deployed on the fighter jet, then it will find out the height of the fighter jet. So altimeter antenna will find the height. It is deployed. It is on the surface of the either missile, or it will be on a fighter jet, or there will be GNSS antenna. So if missile will take longer path, like it is a anti-continental missile, so it will have a flight of 2,000 kilometer or 3,000 kilometer. Then precise trajectory should be needed. So for that we are having GNSS transmitter as well as receiver. So GNSS stands for Global Navigational Satellite System. So depending upon which country it is, like if Indian missile is there, then it will use Gagan, or it can use GPS. So depending upon the country, they will use different navigational satellite system. Like if US will be there, then they will use GPS system. So GNSS transmitter and receiver will be there. Then very important thing you see at the neck of the missile, that is RF seeker or millimeter wave seeker. So this is nothing but a RF sensor or simply RF radar. So this seeker will find out, or it will transmit the signal, and it will find out the reflected signal from the target. Once the target is located, it will find its velocity, then it will find its range, and it will lock on the target. Once the target is locked, then it will follow that target. So this is very important. That is RF seeker. Then we are having a telemetry transmitter. So different systems are there, subsystems are there in a missile, and the data of that subsystem to be sent to the Earth station. So telemetry antenna or telemetry transmitter antenna is used for this purpose. So various antennas are there for complete system. This is the case of missile. Now we will see this is our Indian missile, that is BrahMos missile. These are the various cutout of the BrahMos missile. So at the neck, or you can say at the neck of antenna, we are having RF seeker. This is the expanded view of RF seeker. So it will have a this at the can you see? Sorry. So at the neck we are having the RF seeker. So I will explain more about RF seeker in next slide. So this is the this kind of various missiles are there, and in the missile we are having RF seeker. So this is the head of one of the missile, which is using the seeker antenna. For seeker antenna, we are having a array of 7 hemispherical helical antennas. You can see this green one is helical antennas. So we can use either slot antenna or any other antennas. Most of the time, slot antenna or array of helical antennas are used for a seeking purpose. Seeking means we want to detect the target by illuminating the target. This will act as a radar to find the velocity, to find the trajectory of the target, and to lock the target. There are also optical instrument in seeking. So two kind of seeking will be there. One is RF seeking and second one is optical seeking. So when optical seeking will be there will be a camera, camera as well as there will be a RF seeking or simply RF sensor like this one. Then these are the various term for antennas or antennas on the missile that already I have told you. So RF seeker will see the seeker is essentially a high-tech microwave radar mounted on the nose of airborne system. The RF seeker can track the target in angle, velocity, and range. So based on the designation given in the angle, velocity, and range, the seeker detects the target, subsequently locks on it, then it will goes into tracking mode. So these are the various terms used in the missile. Now there are antennas. There are hundreds of antennas in any satellite. So this is the first satellite that was launched by Russia in 1957. So the name of this satellite is Sputnik. You can see the four antennas. These are monopole antennas. Next is any communication satellite. This is the communication satellite. So communication satellite will have many antennas. You can see some of the antennas here. So you can see these two big antennas. These are single axis antenna. Now what are these single axis antenna? And there are multiple axis antenna. There is telemetry antenna. There is a forward omnidirectional antenna. Then single axis antenna. So the single axis antenna, these are the two antennas. You can see like these two antennas, single axis antenna. So single axis antenna, or simply with single axis antenna, a single modulated carrier occupies the whole of available bandwidth of a transponder. So some frequencies are allocated for each transponder, and these frequency, the complete frequency is utilized by this single axis antenna. So single axis operation is used with heavy traffic routes and requires large antenna. So these two large antennas are used for heavy traffic. We are using single axis antenna, which will use the complete bandwidth. It occupies whole of available bandwidth. Whatever the bandwidth available for satellite communication, it occupies all the bandwidth. If large traffic will be there, then we'll route this traffic through single axis antenna. There are also multiple axis antennas. Like at the bottom of this, we are having 32 receive antenna and 15 transmitter element antenna. This will work in S-band communication, and it is left hand circularly polarized antenna. So different antennas are there, 32 receive antenna and 15 transmitter antenna. So used to have this is used to have you can say multiple access. So more than one station can communicate at a time from this antenna. So like one is a Indian Earth station, second one is at America, and third one is at Canada. So if all want to communicate via this satellite, then they can communicate with each other, as well as they can communicate to other users via this satellite, via using multiple access antennas. Then there is telemetry antenna. You can see this long antenna, forward omni antenna. This is for telemetry tracking and command. So when satellite is launched, first of all, this all large antennas are not deployed. So we want to find out the operation, or we want to find out the parameter of other subsystem. So in order to find out the parameter, this parameter should be sent to the Earth station. So this long, you can say this long antenna is used for telemetry tracking and command, this purpose. So this will be the dipole antenna, lambda by 4 dipole antenna. This will be used, or this will be a spherical uh, this will be a helical antenna. Most of them, either we are using the dipole antenna or helical antenna for telemetry taking and command. So various antennas are used for satellite communication. Then this is known to you. This is a Mars Mars rover that is called as Curiosity rover. So it uses high gain antenna. In high gain antenna, this is having an array of 48 patch antenna, circularly polarized. 48 antennas are there in this hexagon kind of a shape, and this is the radome. Inside this, there will be 48 circularly polarized microstrip antenna. So this is the selfie taken by Curiosity and sent to the Earth, and it is showing the high gain antenna, which will work at X band and which will provide gain of 18 to 21 dB. There are also various antennas in this is the fighter jet. Like this will be CCS antenna. CCS is continuous current sheet antenna. So this kind of antenna will provide a infinite kind of band. So this can be used to absorb the signal coming from the enemy. CCS antenna is there. Then there will be satellite communication antenna, and there is, you can say, AESA, that is active electronically scanned array. This is exactly what I was talking about, the seeker antenna. So this will be the seeker antenna, active electronically scanned array radar. So this is kind of a phased array antenna. So we can have a multiple beam and we can track multiple target at a time by using this kind of antenna. So many other antennas are there. This is the view of a radar antenna, and you can see this. This is your antenna system. So this is array of slotted antenna. There are many slotted antennas is there. Then there will be a subsystem, transmitter subsystem behind this antenna. Then this is once again a antenna system, radar antenna system for MiG-29 fighter jet. It is once again the array of slotted antenna. Then this is the mobile phone. This kind of the phone we are using. So this is actually a 3G, or you can say this will be a earlier generation phone. So it will have a printed antenna. You can see we can use any kind of, like, we can use Vodafone, we can use BSNL mobile. So each will have a different frequency band. Airtel is using 1800 band, Vodafone is using 1800 band. So we are able to catch the signal from either BSNL, Vodafone, or Airtel. So different frequency band or different frequency antennas are required, like 900 band antenna, then 1800 band antenna, 2.4 gigahertz antenna, Wi-Fi antenna should be there. So you can see at the bottom there is low band. This is called PIFA antenna, planar inverted F antenna. So this is the microstrip antenna. There is a feed, there is a sorting pin, and larger this larger side, the bottom side will be used as a 900 megahertz band. This antenna is used for 900 megahertz. Then the upper one is used for 1800 megahertz, and these two antenna, there is above this camera antenna, there will be diversity cell antenna. Now what is this diversity cell antenna? So the diversity is used to have to improve the quality and reliability of wireless link. So more than one antenna will be used for like the antenna or the signal will goes to multipath, and because of multipath there will be fading. So if one antenna will be in a faded region, then second antenna might receive the signal which is not going through interference. So we can have the reliability of communication. So the diversity antennas are used for quality and reliability of wireless link. So these are some of the antennas, and this is the 5G mobile. It will have various diversity antennas. It will use more than four or six antenna for diversity purpose. Then it will have other antennas for Wi-Fi, then for GSM, and so on. There is one more antenna called near field communication antenna, NFC antenna. This will be similar to the antenna you are showing in any RF tag. It is made up of number of loops. So inside this black color thing, there will be many number of loops are there. So the near field can be it can be used for near field communication. Now these are some of the application of antenna. Now let us take, we want to design antenna. So designing of antenna involves many things, and it involves much more mathematics. So it is not like you go and simply you design the antenna, you don't know about mathematics. Without knowing mathematics, you cannot design the antenna. So these are some of the fear factors, the barrier for to antenna designer. Like it has to know the complex mathematics, like it have to know, the antenna designer should know what will be the divergence, what will be the curl, what will be the complex integral. And there are some methods like method of moment, then finite element method, then FDTD method. So these are various methods to analyze the antennas, and mathematical tools like these are the operator like divergence operator, curl operator, gradient operator. These all are used to design antenna. So you must know mathematics before designing the antenna. So it is rightly said by the great scientist Albert Einstein that politics is for present, but the equation is for eternity. You must know the mathematics to design any system, to design the antenna. So there are four set of equations which is given by James Clerk Maxwell in 1979. So this four equation has changed the world. these equations are basically derived from various other equations, and the mathematical forms are given by James Clerk Maxwell. So this four set of equations, actually there were 23 equations, but these four set of equations are very much useful for any communication engineer. So all the communication can be explained using these four equations by applying these four equations. So this four equation, you can see two equation is having a divergence operation and two equations are having a curl operation. So what is curl and divergence? So first of all, what is this delta? Can anyone see what? Can anyone tell me what is this delta? What is the mathematical expression for delta? Am I audible? Hello.
Yes, sir, you are audible. Please go ahead.
Okay. Can anyone tell me what is this delta? Mathematical expression of delta?
Sir, please go ahead.
Okay, this will be d by dx plus d by dy plus d by dz. It means what are these x, y, z? So these are the quantity which are x, y, z is the coordinates. We are using different coordinate system like Cartesian coordinate system or polar coordinate system or any other coordinate system, and these are the points in a coordinate system. X, Y, Z will be the coordinates of a Cartesian coordinate system. So this is the point in a space which is having coordinate X, Y, Z. So the delta is something, any quantity which is changing with the space, with space which is having a coordinate X, Y, Z, and the right side we are having something which is changing with the time. So these equations relate the change in space and time, or simply time and space relationship. Some quantity is changing with time and some quantity is changing with space. In the space it is changing. So these are the relation given by the Maxwell. You can see the in right side, like the time varying quantity is the cause of this effect which is in left side. So first equation, let us take minus dB by dt, that is rate of change of magnetic field. If there will be change in magnetic field, it will produce curl of electric field. Changing magnetic field is producing change in electric field. This electric field is changing in a space because it will have d by dx plus d by dy plus d by dz. So this electric field is changing in space. If there will be a time varying magnetic field, then it will produce the electric field which is changing with the space. So this curl operation will tell you that this will curl around, or this will circulate around the cause, or that will circulate around this change in magnetic field. Sorry. Then the next equation, that is first we'll see this del cross H. So J plus dd by dt in a free space, J is equal to 0, that is current density is equal to 0. So del cross H is equal to dd by dt. So the change in electric field, D is equal to epsilon E. So change in electric field will produce change in magnetic field. This magnetic field is circulating around this electric field. So there will be change in space coordinate in magnetic field. This change in electric field is producing change in magnetic field. And the divergence operation tell that whether the quantity is coming out of some point, or it is terminating at some point. If it is coming out of some point, then there will be a positive divergence, and if it is uh, terminating at a point, then there will be a negative divergence. And if the thing is parallel, or we cannot say where it is starting and where it is terminating, then the divergence is 0. This is exactly seen here. Del dot B is equal to 0 because magnetic field is always in a loop. So we cannot say in a loop whether there will be starting position and where will be the ending position. So del dot D is equal to 0, and for electricity, del dot D is equal to rho. So if there will be a volume charge density or surface charge density, then there will be the electric field coming out of that surface. So these are the physical meaning of these four equations. Now, not wasting much of the time, let's see what are the challenges to antenna designer. So, antenna designer, depending upon application, it has to design the antenna. So, the designer must have to follow some criteria, like it should provide some, whatever the gain is required, it should provide the antenna should provide the uh, gain, then it should have a wider bandwidth, then the size of antenna should be small, then it should have a low cost polarization. So these are the criteria, various criteria are there for different applications, and the antenna engineer should meet all these criteria depending upon the application. Now we'll see the fundamentals. So these are the radiation pattern of antenna. Like first pattern is called as isotropic radiation pattern. Now what is this radiation pattern? Radiation pattern is how antenna will radiate in a space. The pictorial representation is called radiation pattern. The first one is isotropic radiation pattern. So in isotropic radiation pattern, antenna will transmit signal equally in all the direction, isotropically in all the directions. So if you will take the cut of any one of them in any plane, it will be circle. So it will transmit equally in all the direction. That is isotropic radiation. So if you take the if you take log of this, because this is equal in all the directions, so you can say 1 in all the direction. No, if you normalize this, then that will be equal to 1. Now if you take log of this, then the directivity will be equal to 0. 10 log of 1 will be 0. So directivity of isotropic antenna, which is written in blue color at the bottom, that will be equal to 0. The second radiation pattern is omnidirectional in one of the plane. It is not isotropic. It means it will radiate power equally in one of the plane. These are the difference: isotropic and omnidirectional. Omnidirectional, it will radiate equally in one of the plane. Like in horizontal plane, if you cut the second radiation pattern in horizontal plane, then it will be omnidirectional. It will have a radiation pattern equal to circle. And if you slice this radiation pattern in vertical plane, then this will have a figure of 8 kind of a pattern. So this is actually a radiation pattern of a dipole antenna. The third is the directional radiation pattern. So it will radiate power in one specified direction, and that are the directional antennas. Now, how antenna will work? So there will be a transmitter, or you can say a generator, and transmission line. Transmission line will carry your power from one point to other point, and so this can be a waveguide, or this can be a cable, depending upon the power requirement and the frequency of operation. We can use cable or we can use a waveguide. Now, which will carry the signal from one point to other point. Now, if the separation will be not there between the transmission line, then the electric field and magnetic field will cancel out each other, and there will be no radiation. If we flare our transmission line or waveguide, then it will act as an antenna and it will radiate the signal. In order to survive in the free space, signal must be in a form of a loop. So this is showing how the loop will be generated. Once loop is generated, this signal will be detached from the antenna and it will propagate freely in the free space. The radiation pattern will have a different parameter, like the beam width of the radiation pattern. In beam width, we are having half power beam width, first null beam width. Then there are lobes: major lobe, minor lobe, side lobe, back lobe. So beam width between HPBW, that is called as half power beam width. These are the points on the antenna characteristic, the antenna radiation pattern, which is 3 dB down to the maximum. These points are 3 dB down to the maximum. That's why this is called half power beam width. The width will be in form of an angular spacing. Then first null beam width. These are the difference between two nulls. The beam width between two nulls. It means the angular separation between two nulls. Then front to back ratio. The ratio of maximum transmission in the front side to the back side. So front to back ratio, The antenna should transmit maximum toward the front side, so front to back ratio should be higher. These are the radiation pattern in a 2D form. So it will have a maximum at the theta is equal to 0, and these are the side lobes. The half power beamwidth is shown, then first null beamwidth is shown. Now antenna field zone. Let us take this is the antenna, and the antenna is radiating. Now near antenna, it will have electric field and magnetic field. Now this magnetic field is changing very rapidly. So this oscillation takes place very, so depending upon frequency, this oscillations is created, and at the near of antenna, it will be reactive kind of a field, which is not useful for a far field kind of a thing, or we are not using this reactive field. We cannot have any information from reactive field. If we move further from the antenna, then there will be one region called radiating near field, that is also called as Fresnel's region, which is given by 0.62 under root d cube by lambda. This much distance, this is the boundary of radiating near field. So near in this radiating near field, our antenna patterns start to develop. In measurement for very large antennas, we are using this kind of field, that is Fresnel region, to find out the radiation characteristic of antenna. And there is third, that is far field pattern, or that is also called as Fraunhofer region. The Fraunhofer region is given by, the boundary of Fraunhofer region is given by 2d square by lambda, where d is the largest dimension of antenna. If it is the length, the dipole is shown, then the length of dipole is the d. D is considered to be the length of dipole. So 2d square by lambda is the far field boundary. So antenna must be in a far field region. We are interested in far field characteristic. This is the same thing as depicted in earlier figure. So this is the antenna. The near field distribution is there, which is very oscillating. So we are not using this near field distribution. Then there will be radiating near field. You can see the our pattern start to develop, and we can use this pattern. And there is at very large distance, we are having a far field. So actual radiation pattern will be there in a your far field zone. Now there are some definition like what will be the gain of antenna. If you are an antenna designer, then there are requirement like your antenna should be having this much gain. It should have a cross polarization, this much cross polarization, and it must have a S11 down to 10 dB or down to 15 dB depending upon your requirement. So what are this parameter? First one is gain. Gain is radiation intensity of antenna gain in given direction over that of isotropic antenna. So you can see this, there is an antenna and there will be a red dotted line. This is the radiation intensity of a sphere, or you can simply say this is the radiation pattern of an isotropic source. Now there will be a second antenna which is at the center of this, and you can see it is transmitting a directional beam. So all the directivity or gain we are measuring with respect to isotropic antenna. It means how much more this particular antenna is radiating with reference to isotropic antenna. If there will be isotropic antenna, then it will radiate equally in all the direction, like shown in dotted line, red dotted line. If we are using other antenna, then it is transmitting more in some direction, and this more with respect to isotropic antenna is called as gain. It is radiation intensity of antenna in given direction over isotropic antenna, that is called as gain. The equation of gain is 4 pi AE by lambda square. Now what is this AE? AE is called effective aperture. So gain is directly proportional to effective aperture. More the effective aperture, more will be the gain. So you are seeing the large antenna like reflector antenna. These reflector antennas are having the largest gain because very large reflective antennas can be possible, and it will provide point to point communication. So very pencil beam kind of antenna will be there. It will have a beam width of 1 degree, 2 degree, depending upon size. So large gain can be possible with large aperture. Smaller the aperture, smaller will be the gain. The directivity and gain. Directivity of antenna is ratio of radiation intensity in direction of maximum radiation to the density average over all the direction. So this is the ratio which is given by this equation, maximum radiation intensity in given direction divided by average radiation intensity. The relation between gain and directivity is gain is equal to efficiency times directivity. So directivity and gain are related with efficiency. If we are not taking consideration of efficiency, then we can give this will be in terms of directivity. Various kinds of beams are possible. Like these are the beams used in radar, like pencil beam. Very narrow pointed beam will be there, and which will have a beam width of 1 degree or 2 degree. Then there is a fan beam. We want to scan some geographical area, then we require to scan the vertical axis more. We want to scan more in vertical direction, then we can use fan kind of beam. Or we want to uh, have a multiple target. We want to detect multiple target, then we can use this take beam kind of a thing. Then we can also use shape beam. So these are various kinds of beams used in a antenna, specifically in a radar. This already you know what is VSWR, that is voltage standing wave ratio, what will be the reflection coefficient. So I am not going into detail. The polarization is very important thing, that is called as orientation of electric field vector in a space and time, that is called polarization. How your electric field is varying in space and time, that is your polarization. So three kinds of polarizations are given here: linearly polarized, circularly polarized, and electrically polarized antenna. So two linearly polarized means we are having either vertically polarization or horizontal polarization. In vertical or horizontal polarization, the electric field signal will vary either vertically or horizontally. That is your linearly polarized. If your signal is moving in a space and it is circulating around a point, then that is called as a circularly polarized signal. If it is elliptically rotating, then that will be called elliptically polarized wave. Now, this is the equation where E theta and E phi are the amplitude, and A theta, sorry, E theta and E phi are the electric field, and this alpha is the angle. So, if two linearly polarized waves are there, and if these two are added, then different kind of polarization can be possible. So, you can see if I want to have a circularly polarized wave, then I can go for two linearly polarized wave having equal amplitude, that is E theta and E phi should be equal, and the, the angle between these two are 90 degree, that is plus or minus pi by 2. Then we can have a circularly polarized wave. If the amplitudes are not equal and we are having any other any other angle, it can be also pi by 2 or any other angle, then it will result into elliptically polarized wave. You can see different polarization here. So first one is electromagnetic wave. You can see the blue line, that is the magnetic field, and red lines are electric field. At the bottom of this, you can see the wave is moving in one direction. It is made up of red and blue. When you join these two together, and if the amplitude are same and if angle is 90 degrees, then it will result in the circularly polarized wave. So this wave is moving in minus z direction. You can see the wave is moving in minus z direction, and to find out the polarization, we have to see from plus z direction to we have to see from the backward of the wave. If the wave is in anti-clockwise direction, then that is called as left hand circularly polarized. And if it is in a clockwise direction, wave is moving in a clockwise direction, then that is called as right hand circularly polarized wave. So right hand circularly polarized wave is shown in this green color signal. So the wave is moving in a clockwise direction, so that is right hand, and Here left hand circularly, so left hand as well as right hand both are shown here. Right now it is left hand circularly polarized. Next we will have a right hand circularly polarized wave in a green color signal. We'll see the half wave dipole. Now what is this half wave dipole? We'll see first this. So this is the dipole. The electricity is restored. Let's I will take 2 minutes. I will connect with internet from my PC. Hello.
Yes, sir.
I'll take 2 minutes. I will change over from my mobile phone to PC. Right?
Okay, sir.
There is internet problem. So we'll continue from mobile only because there are some internet issues.
No problem, sir.
Okay. So this is your dipole. What is actually a dipole antenna? Dipole antenna is a wire antenna which is made up of a wire. We can use different length of a dipole for our antenna purpose. So we can use either lambda by 10 dipole, lambda by 2 dipole. The length of the dipole antenna will be either lambda or 1.5 lambda. So or any other length of lambda is possible. So half wave dipole is the simplest dipole, which will have a upper arm and lower arm, or simply it will have a two arm. Depending upon length of dipole, it will produce different directivity and half power beam width. So these are the equation for the dipole antenna. You can see E theta and H phi field are given. These are the far field. If you take the ratio of E theta and H phi, then it will give us eta. It will be equal to 120 pi. So this is E theta H phi, and from this, if you plot, if you find out the directivity, then the directivity is around 1.643. It means it is it is radiating more power 1.63 times more power compared to isotropic antenna, or in terms of dB it will be 2.1 dB, and the radiation resistance of this dipole is 73 plus J 42.5. It is not equal to 73 ohm. It is the complex thing 73 plus J 42.5. So when we calculate the length of dipole, let us take I want to design a dipole for 10 gigahertz. Then lambda for 10 gigahertz is 3 centimeter, and lambda by 2 will be 1.5 centimeter. So I will not exactly choose 1.5 centimeter as my length for 10 gigahertz, but I will make them smaller than 1.5 centimeter, because we are having the complex that is plus J 42.5. It means we are having some inductive portion. In order to minimize this inductive portion, we will reduce its size less than lambda by 2. It means we'll reduce to, will not use as 16 what was that 16 mm, but I will use, instead of this I will use either 15 mm or less than that. Okay, so we'll reduce the size in order to nullify the effect of this complex quantity J 42.5. These are the radiation pattern, and you can see in the middle of the middle curve is showing the radiation characteristic. So you can see the blue line is for isotropic. If there will be isotropic, then it will radiate 0 dB of power. It means it will have a equally power in all the direction. While we use the dipole, then it will be having a gain of 1.643. It means slightly more than the isotropic antenna. In this blue line in a first figure, this blue line curve is showing, this blue line curve is in horizontal pattern, and this red line is vertical pattern. It means in one of the pattern it is a isotropic, it is omnidirectional in the nature, and in vertical plane it is a directional, which is having a figure of 8 kind of a radiation pattern. All the mathematical terms for this half wave dipole is given at the bottom of this. You can see different length of dipoles are there. You can find out the directivity as the size of dipole increase, the directivity will increase, and directivity will be maximum for 1.25 lambda. If you goes on increasing the length of dipole, the directivity will not increase every time, but the maximum directivity will be possible at 1.25. Then some losses are there, and this losses will decrease your directivity. So overall maximum directivity will be available when you use 1.25 times lambda of length. And you can find out the half power beam width. For lambda by 10 it is 90 degree, then for lambda by 2 it is 78 degree. It means more the length of your dipole, it means effective aperture will be more, then gain will be more the gain, your half power beam width will be small. So as length is increasing, the directivity is increasing, but the beam width is decreasing. Now we will not go into this detail. Let us take, you want to design a 900 megahertz, then what will be the length of antenna, what will be the diameter of dipole, and what will be the effect of this diameter, and which are the properties to be observed. So the length of dipole will be equal to, the calculation is given, it will be lambda by 2. So 3 into 10 raised to 10 divided by 10 raised to 6. So this will give us 33 centimeter, and the lambda by 2 will be 16.66 meter centimeter. Will use slightly less than this, and the diameter will choose smaller as possible. If you increase the diameter, then the gain will increase, sorry, the gain will slightly decrease, but its bandwidth will increase, as well as the efficiency will decrease. So if you want more bandwidth, then you can go to increase the diameter, but the efficiency of this dipole will decrease. This is these are the radiation pattern. This is first of these are the parameter we're looking for any antenna. First one is a return loss. Return loss for any antenna must be less than 10 dB down, minimum 10 dB down. It must be minus 10 dB down. Lesser the return loss, more good will be the antenna. So the return loss will tell us, if we are giving some signal, how much signal is returned back to the transmitter. So we don't want any signal to be returned back to the transmitter. We want most of the signal to be transmitted in a free space. So this should be as low as possible. Then this is the 2D pattern, and this is the 3D pattern. This red one will be the 3D pattern. If you cut this 2D pattern, this 3D pattern in horizontal plane and vertical plane, then this will give you, if that will give you the omnidirectional or this figure of 8 kind of a thing, radiation pattern. Then most probably these monopoles, we have seen the dipole which are having a two arm, the upper arm and lower arm. The overall length of the antenna is lambda by 2. If we use the one arm of the dipole, then that will be called as monopole antenna. In dipole we are using lambda by 2. In monopole we are using half of the dipole. We are using only one arm of the dipole. So that is called as quarter wave monopole antenna. We are not using full lambda by 2, but we are using half of that. So this is called quarter wave monopole antenna. This kind of antennas are used everywhere, in your mobile, in your mobile, then mobile tower, then satellite, everywhere these kinds of antennas, in your car, everywhere we are using monopole antenna. Why we are using monopole antenna? Because it will have a double gain compared to the dipole antenna, as well as it will provide us omnidirectional similar characteristic that is provided by dipole antenna. It means in horizontal direction it will be omnidirectional, and in vertical it will be a directional characteristic. So to analyze the quarter wave monopole antenna, we are using the theory of image. It means this is quarter wave dipole, and at the bottom there will be a infinite electrical conductor. If there will be infinite electrical conductor, then we can use theory of image. It means the complete, this is only a half dipole, but the image of this dipole will be there at the opposite side. So this will work as a lambda by 2 dipole, but actually the length is lambda by 4. So the equivalent of this dipole is shown left side. Overall this will be lambda by 4 at the upper side, and the image of this lambda by dipole is at the bottom side. So overall, this will act like a half wave dipole. Its impedance will be half of the previous, that is half of the dipole. We are having 73 in dipole antenna, and here in monopole 36.5 plus J21.25, and the directivity will be the double of the dipole. In dipole we are having directivity that will be 1.643, while here it will have a twice the directivity. Now what will be the effect of radius if we are varying the radius of monopole? What will be the effect? So you can see as the radius of monopole increases, its inductance, this is the Smith chart. The upper one in a Smith chart is the inductance, and bottom is uh, bottom one is conductance. So if we goes on increasing the radius of monopole, the inductance decreases and impedance plot shifts to down. And in case of bandwidth, as radius of monopole increases, you can see different line. The resonance frequency decreases slightly, but bandwidth increases significantly. You can see the table. We are having for different radius changing from 0.5 mm to 10 mm, and you see the bandwidth. The bandwidth is changing from 12.4% to 42.1% in with radius is equal to 10 mm. So bandwidth increases with increasing radius of monopole, or bandwidth also increases if you goes on increasing the radius of dipole also. Now more the diameter, or you can say more the radius, more will be the bandwidth. Now we are making this folded one. So actual length is L or lambda by 4, but we are folding this. So this is the folded or inverted dipole. Second one is folded or inverted dipole. Or still we want to minimize the length, then we are short circuiting it with the ground. Then the once again length will decrease by lambda by 4. So we are having a lambda by 4 dipole. Then if we do the inverted F antenna, that is we are sorting this with the ground, then it will provide us, it will be having half of the length compared to inverted L and inverted L antenna. This inverted F antenna will have half of the length compared to inverted L antenna. Then we can use helical antenna. Helical antennas can be used for normal mode application. In our mobile or in our car, we are using the helical antenna in a normal mode operation. There are two kind of operation in a helical antenna. One is called axial mode, and second one is a normal mode. In normal mode, it will behave as a dipole whose diameter of a helix will be smaller than lambda by 2. Then it will operate as a normal mode helix. In axial mode, the diameter will be greater than lambda by 2. Then it will have a circular polarization, and this will having a different radiation characteristic compared to the dipole. So these are some of the monopole antenna, or these are the antennas used in our mobile phone. You can see the earlier generation antenna, we were using this dipole, we were using this monopole. So different, this monopole is detached from the this antenna. So earlier generation antenna you might have seen or not, I don't know, but the antennas were there which is visible to the eye. This is the back side of this mobile phone, and this is the different generation of antenna. This is the first, this one is the first mobile phone given by the Motorola. This is the first mobile phone used by human, which is developed by the Motorola, and this is the developer of this phone. He is the Martin Cooper from Motorola, and the phone name is the Motorola Dynatec 800. The weight of this phone was around 1.1 kg at that time. It was around 1.1 kg, and you can clearly see the antenna. This is lambda by 4 antenna. Then you can see different kind of antennas. So earlier generation we were using lambda by 4 antenna. Then we started to use microstrip antenna. So that antenna will be fit inside the dipole. These are the external antenna and these are the internal antenna. Now we are using microstrip antenna. In microstrip we are using P5 antenna, planar inverted F antenna. So it will reduce in the size, and we are using many antennas. These are briefly for communication, and we nowadays we are using many antenna inside our smartphone. We are using 5G communication. In 5G communication we must use MIMO. So at least 2 cross 2, it means 4 antenna will be there for diversity purpose, as well as there will be antenna for communication for GSM 1800, for GSM 800, CDMA. Then there will be antenna for Bluetooth, there will be antenna for Wi-Fi, and so on. So many antennas are there in mobile phone, and some of the antennas I have already earlier shown these antennas. P5 antenna 1800, and there is, so this is all about mobile phone antennas, or simply the dipole and monopole antennas. These are the vastly used wired antennas. Then we'll move to other antennas like Yagi Uda antenna. I will move very fast now because time is very less with us. So this is the Yagi Uda antenna. It is array of dipole. So only one antenna will be fed, and rest of the element will act as a passive element. So this driven element is fed with the power, and this director element will provide the gain, while reflector element will provide the reflection. So it will reflect the signal in forward direction. So we'll have a highly directional antenna which will have, but this kind of Yagi Uda antenna will have a small beamwidth. The direct, it will be highly directional, but bandwidth will be small. This is the problem with the Yagi Uda antenna. We'll move faster. Will not go into the detail of this. Then there will be aperture kind of antenna which will use the rectangular or cylindrical waveguide. This is the rectangular waveguide which will have a dimension in larger dimension in horizontal and smaller dimension in vertical, and these are various modes. The fundamental mode, or the mode which is having the lowest propagating, lowest frequency, lowest cutoff frequency, that is called as fundamental mode. So TE10 mode is fundamental mode. So modes are nothing but various configuration of electric field and magnetic field line that can propagate inside your waveguide. So lowest mode which is propagating inside the waveguide is TE10 mode. In a rectangular waveguide, this TE10 mode. There are various horn antennas, like if you flare your waveguide in both the direction, vertical as well as horizontal, then that will become your pyramidal horn antenna. If you flare your horn in one of the direction, then that will be your E-plane sectored horn antenna. If you flare in H-plane, then that will become H-plane sectored horn antenna. And if you are having a cylindrical waveguide, then that will be your conical horn antenna. So this is the one of the pyramidal horn developed at 10 gigahertz. You can see the electric field is moving from, this is at the waveguide, to the aperture of the antenna, and these are the radiation patterns. So this will be a highly directional antenna. We must first of all find out the return loss of the antenna, and you can see the return loss is better than 17 dB at each and every frequency. Sorry, this is the radiation pattern in this is the radiation pattern in E as well as H plane of this antenna. You can see this M2 point. This is called cross polarization pattern. This M1 point, or simply this kind of pattern, is called, which is having a maximum at theta is equal to 0. That is your radiation pattern, which is called copolar pattern. And the radiation pattern which will be 90 degree to this, that is called cross polar pattern. This is the pattern you can see in a gray line. This should be minimum. If you are using frequency reuse concept, then this should be minimum. So M2 should be less. The peak of the cross polarization pattern should be very much less. Then these are the modes in circular waveguide. The fundamental mode is called TE11 mode. This is the mode which will having the lowest cutoff frequency, and these are the higher order mode. So I'm not going into the detail of this design. So this this part is called aperture of the horn. So larger the aperture, you know that from the gain equation, G is equal to 4 pi A by lambda square, 4 pi A by lambda. So gain is proportional to directivity, but it is not always true. You can see this. This is the gain curve, universal gain curve for the conical horn antenna. You goes on increasing the horizontal plane, horizontal line is for the various diameter of aperture. It means you are going on increasing the diameter of aperture, and the vertical is directivity. You can see that the directivity is first increasing as you goes on increasing the diameter, and then it will start decreasing. This is because of the losses. Losses uh, because of the losses, this directivity will decrease. So it will have a peak directivity at some point, and that directivity, if we design our antenna based on the peak directivity, then that is called as optimum horn antenna. So the design equations are given, like we'll first choose the radius of the radius depending upon the frequency, that is 3 lambda c divided by 2 pi. From that we'll select the radius, then we'll find out the radius of aperture depending upon what gain we require. Then we'll find this radius, and let us take, we want to design 13 dB antenna, then we'll take the radius is equal to 14.3 for 10 gigahertz. This radius is selected for 10 gigahertz, so we'll choose 14.3 as a radius for this aperture antenna, and these are the simulated result. You can see how field is moving and how TE11 is there at the aperture of the horn. This is return loss. Return loss is everywhere minus 22.5 dB down, and this is the radiation pattern 3. This is and these are the radiation characteristic at different frequency, like 8 gigahertz, 9 gigahertz, 11 gigahertz, and 12 gigahertz. Now there are some problem with this. All antennas are called smooth wall antennas because the inner wall is smooth. Now because of this smooth wall antenna, it will have a larger cross polarization, as well as it will have a the radiation pattern are not symmetric. So many application, like in a satellite communication and other application, we require the symmetrical radiation pattern. It means in all the direction the radiation pattern should be symmetrical, and we require minimum cross polarization. So if our requirement are such, then we are going to use corrugated horn. So this is the cutout view of corrugated horn. So inner wall are corrugated one. So this kind of horn will produce the symmetrical radiation pattern. We are not going into detail because we do not have a time. It requires much more time. So this is the simulated sorry, this is simulated results of the corrugated horn. You can see the electric field at the input of antenna. We are having TE11 mode, but at the aperture of horn we are having HE11 mode, and because of this HE11 mode, the radiation pattern are symmetrical in all the direction, as well as it will have a minimum cross polarization. This green one, this is around minus 40 dB down to the peak of the copolar region. So this radiation pattern is a symmetrical in all the plane, as well as it will have a minimum cross polarization. So we are using corrugated horn for such application. Then we have this microstrip patch antenna. So microstrip patch antenna, you know that it will have a 3 layer. One is a ground plane, then uppermost will be the patch, and in between these two there will be a substrate. So these are this kind of antenna nowadays widely used. These are various kinds of a patch antenna. Various shapes can be possible for patch antenna. It can be a rectangular antenna, it can be a circular antenna, or elliptical antenna, or E-shaped antenna. Different kind of patch are possible. It will have a different advantages, like it will the fabrication is very easy. It will easily provide circular polarization. Then it will be lightweight, low volume, and low profile kind of antenna. Then the disadvantage are this kind of antenna is having a very small bandwidth. So it will have a narrow bandwidth. Then it cannot handle large power and poor isolation. surface waves will be excited. These are the disadvantage of this kind of antenna. But the advantages are very high, like lightweight, then low fabrication cost, and so on. So these antennas are finding very large application nowadays. These are the design equation. Will not go into detail of this design equation. Simply see this F0 is equal to C by 2 under root epsilon E. So this epsilon E is your substrate permittivity. So the frequency will depend upon, the frequency of operation will depend upon, that will be inversely proportional to uh, substrate permittivity. If we are having a small substrate permittivity, we are using substrate with less substrate permittivity, then F0 will be inversely proportional. It means smaller epsilon r, then F will be larger. If F epsilon r will be larger, then F will be smaller. So once again, these are the design equation. Smaller or larger width can taken the, so in your equation we are having L and W. Larger the width, more will be the bandwidth, and L should be approximately equal to lambda by 2. So smaller or larger W can be taken. Bandwidth is directly proportional to width, as well as gain is directly proportional to width. So we have to design antenna by using this equation, and by changing the width we can have a different bandwidth. This is the simulated microstrip patch antenna. You can see this is designed for 900 megahertz, and you can see it is resonating at 900 megahertz. So minus 10 dB, this return loss source minus 10 dB around 900 megahertz, and this is the radiation pattern of this antenna. And this is the current, uh, what you can say, the field distribution, magnetic field distribution around antenna. Now, what will be the effect of width? As I have told you, as you goes on increasing the width, the gain will increase as well as bandwidth will increase. These are some of the table. We are changing the dielectric constant from 1 to 9.8, and you can see the gain is changing from 10 to 4.4. So the gain will decrease, but with the decrease in epsilon r, both length and width will increase. With increasing fringing field and aperture area, so bandwidth and gain will increase. If you increase epsilon from 1 to 9.8, the gain will decrease, but bandwidth will increase. The compact MSA is possible. This is the MSA, that is microstrip antenna for TM10 mode. So at the center of TM10 mode, you can see the field component is 0. So we can remove this half portion because field is 0 at the center. Instead of this, we can apply a short circuit. It means we can provide a wire to the ground, and we can make the compact antenna. We can use half of the length. So this is the principle behind planar inverted F antenna. We are using only half of the length compared to L by 2 length used in microstrip antenna. We are using now half of the length. We are providing short circuit. It means we are providing the sorting pin from ground to the upper part of the patch, so that the overall length will decrease. It is called planar inverted F antenna. Then there is reflector antenna. So this will be the last thing. Then we will wind up. So reflector antennas will provide most of the gain. So reflector antenna you have seen in the satellite communication at the Earth station, as well as at the on-board satellite. We are having the reflector antenna because the reflector, it will provide most of the gain, because our satellite will, let us take it is geosynchronous satellite. It will having the it is 36,000 kilometers above our Earth. So it should have, in order to communicate, we require the precise, or we require very large gain for point-to-point communication. So we are having a parabolic reflector, and in parabolic reflector we are having a different different kind of a parabolic reflector. So parabolic reflector, this is the parabolic front-fed parabolic reflector antenna. The parabolic reflector antenna will have a focus, and whatever the wave emitting from this focus will provide a plane wave at the aperture. So it will provide a maximum gain, because at the aperture it will provide the plane wave. So it will convert your spherical wave to plane wave. If we are using this kind of configuration, that is called front fed configuration, where our feed is at the focal point of the parabola, then it will provide the gain, but the feed will have a finite size and it will obstruct the forward path of the reflected wave from the parabola. So it will have a smaller, it will deteriorate, it will have a larger side lobe, as well as it will have the loss in gain, or directivity will be less. This particular thing in the left hand side is showing that, let us consider we are having a vertically polarized wave, then the vertical lines is for vertically filled, and the horizontal lines are for the cross polarized field. You can see this is a symmetrical parabolic reflector. So there are the vectors which are 90-degree in adjacent quadrant. In all the quadrants, the horizontal component are 90-degree to each other, 180-degree to each other. So they will cancel out each other, and there will be very small cross polarization. This is the biggest advantage of this. It will provide very high gain and it will have very less cross polarization. So this is the simulated uh, results of this antenna. You can see this is a 40-meter reflector, 1-meter reflector. It will have a gain of 40 dB, and this pink one shows the cross polarized signal. So cross polarization is very less in case of a front fed parabolic reflector antenna, and these are called the contour diagram of this radiation pattern. You can see in 45-degree below this antenna, you can see the 45-degree we are having the cross polarized field, and this green one, it is the co-polarized contour plot. So at the center we are having maximum field. This red line, this red circle at the center, it means we are having a maximum field at the center. Then because we are having the feed is obstructing the field, so in order to overcome this, we are using offset parabolic reflector antenna. So we are using the part of parabolic reflector antenna, and we are using feed at the focal point, but we are using such a way that field will the feed will not obstruct the path of reflected field. But because of this, now the cross polarization field, which was, you can see in case of parabolic reflector, this front fed parabolic reflector, this here the cross polarization field is cancelling each other, because these are 180-degree out of phase. Now when we use front fed parabolic reflector antenna, this cross polarized field will not cancel out, because this is asymmetrical in nature. So 180-degree cancellation will not be there, and because of that, you can see this blue line and pink line. These are called cross polarized field. So this is very high, and this will depend upon the offset angle. Larger the offset angle, more will be the cross polarized line. We want to reduce this cross polarization if we want to use for frequency reuse purpose, as well as for other purpose. We must reduce this line. So you can see the contour plot at the bottom of this. The cross polarized field now are in 90-degree plane. Previously in front fed parabola, they were in 45-degree plane. Now it is in a 90-degree plane, and these are the at the bottom of the radiation pattern. This is radiation pattern contour plot. This is the copolar radiation pattern contour plot. So at the center it will have a maximum and less at the other side. There is other configuration also, that is called as Cassegrain parabolic reflector antenna. In Cassegrain parabolic reflector antenna, instead of using now Cassegrain will use sub reflector. It means it will have a one more reflector. The sub reflector can either be hyperbola or it will be ellipse. If you are using hyperbola, then that will be a Cassegrain reflector, and if you are using ellipse as a sub reflector, then that will be a Gregorian reflector. So this kind of antenna will provide the larger gain. We can place our antenna at the convenient position behind the antenna, and we can illuminate the sub reflector by the feed. So we are having the convenience to place our feed or we use very large field also, or array of field also can be used for this purpose. So this kind of antenna will illuminate our reflector, main reflector, parabolic reflector, uh, and it will provide more gain. So this is the simulated output of a Cassegrain antenna. You can see the cross polarization is very much low, as well as it will have a higher gain. So we are not going into detail of this measurement. Hello,
Yes, sir.
any questions?
No, sir, no problem.
I have taken 15 more minutes.
No problem, sir.
Okay. Are there any questions? The designing of each antenna requires at least, or in order to explain, I require at least half an hour for each antenna. But we have wound up in 1 hour, so very less time is allocated to each antenna.
Yes, sir.
Only we have done the overview of types of antenna and how the designing can take place. We have seen only the overview.
Yes, sir. So the session was very informative, sir. You
Thank
covered
you.
all the practical applications from satellite communication to the basics up to 7th and 5th sem students. You connected the industry to the at the student level, sir. The session was very informative, sir.
Okay.
Hello, sir.
Thank you, ma'am.
Yes.
Yes.
Okay, sir. Sir, we would like to end up this session now.
Okay, ma'am.
Okay. Okay.
Thank you, ma'am.
Thank you, sir.
Okay. Kindly send the report once it is finished.
Yes, sir.
Okay. Thank you, ma'am. I'm ending up.
Yes, sir. Okay, sir.